All right, so we're going to take a look at some problems involving buffers and pKa and pH. That's a typo. I should say pH, not pJ. Okay, so first thing I'm going to do is I'm going to calculate the pH of some solutions. And in this set of problems, we kind of give you a big spoiler when we say, hey, this is a buffer, but you won't always be, told explicitly that it's a buffer. So you want to recognize when you have a buffer. And remember, a buffer is a combination of a weak acid and its conjugate base, or you could think of it as a weak base and its conjugate acid. That's what makes a buffer. So you want to recognize that, okay, HC2HO2, this is an acid, and this right here, when I dissolve it in water, it's going to break apart and form these two ions. And this right here, CHO2 minus, is the conjugate base of this acid right here. So this is a weak acid and conjugate base, so I have a buffer. And that's important to know because if you have a buffer, then you can use this equation right here, which is found on your equation sheet. You don't need to memorize it. It's right there for you. pH equals pKa log A minus over HA. It's also really important to identify which is which and make sure you're, putting these molarities in the right spot. So let's go through this one. So the pKa is the negative log of the Ka. And there's some Ka values that are given to you on this page. So for formic acid, the Ka is 1.8 times 10 to the negative 4. And then log, and I'm going to put the base is the sodium formate. So that's 0.15 molar, that's the base. And then the acid is the 0.2 molar, the formic acid. And so I'm just going to now stop and plug this in my calculator. So 1.8 e to the 4 negative. Log of it. So my pKa is 3.74. Your pKa should always be a little bit less than whatever this exponent is. So it's like a little bit less than 4. And then plus the log of 0.15 divided by 0.2. Take the log. And it is a negative number. Plus 3.74. So you end up with a pH of 3.62. And a reminder, when you have a buffer, a pH equals the pKa if the amount of weak acid and conjugate base are exactly equal. In this scenario, they're not exactly equal, right? And notice we have a little bit more of the acid component than the base. So notice the pH ends up being a little bit less than the pKa. So 3.6 a little bit less than 3.7. So that's something to be aware of. All right, so now let's take a look at this one. Again, we have a conjugate acid-base pair. So NH4 plus is my acid, NH3 is my base. And so to find the pH, I'm going to take the pKa. So I'm going to take the negative log of the Ka, which is right here. Here's my ammonium Ka. So it's 5.6 times 10 to the negative 10. And then the log, and I want to make sure we put base over acid. So the base is the ammonia, that's 0.16. The acid is 0.22. Once again, I got more acid than base here. So I'm going to plug this in my calculator. So the pKa is 9.25. And then 0.16 divided by 0.22. I take the log of it. It's negative 0.14. 9.25. Boom. 9.11. So there is your pH there. And again, look at these buffers. These are both examples of buffers. And for a buffer, the pH is going to be close to the pKa. So this case, the pH is close to 9. This pH is close to 3 or 4. So buffer does not mean neutral. So notice that neither of these are neutral. They're not pH 7. But what makes something a buffer is that it's going to maintain this pH. So like this solution, if you add additional acid or base to it, the pH is going to stay at 3.6. And this solution is going to stay at 9.1. That's what makes it a buffer, is it resists changing pH. So let's take a look at this one. If you're looking at benzoic acid here, so that's this one, HC7H5O2. It's a weak acid. So it's going to dissociate here. And so I could find the pH by setting up an ice chart. So I'll just do that real quick. 0.15 minus x. All right, and then my Ka is my products over my reactants. And I know the value of Ka is 6.5 times 10 to the negative fifth. And so I can rearrange and solve here. So 6.5 E times 0.15 square root. I end up with X being 0.0031 molar. That's my hydrogen ion concentration. So I take the log here and I get the pH, which is going to be 2.51 here. So that's my pH of pure benzoic acid. All right, now let's look what happens if you mix together benzoic acid and sodium benzoate. So that is your weak acid and your conjugate base. So in this case, it's a buffer. So I can use this equation, pH equals pKa log of the A minus over the HA concentration. So the pKa is the negative log of the Ka, which for benzoic acid is 6.5 times 10 to the negative fifth. And then the benzoate is 0.1. This is 0.15. So I'm going to stop and plug this in my calculator. 6.5 E log. So my pKa is 4.19. And then I have negative 0.18. And this one's up being 4.01 is your pH there. So which solution has more H plus ions? Solution A has more H plus ions, and one way you can justify that is because it has a lower pH. So lower pH means it has more H plus ions. But it says explain why this is in terms of equilibrium. So let's go back and kind of look at this equilibrium system. So this right here just shows benzoic acid dissociating in pure water. Okay, and it makes this many hydrogen ions that got a relatively low pH. Down here, we're thinking, what if benzoic acid is actually combined with sodium benzoate? So this right here, this is the benzoate ion. So what this is situation B, your buffer is a common ion situation. So what that means is when you're trying to, your HA is dissolving in a solution that already contains some A minus ions. So this right here would be your benzoate ion, and this right over here would be your benzoic acid. So because you're dissolving benzoic acid in a solution that already has some benzoate ions, this reaction is not going to proceed as far due to the common ion effect. This is something we talked about, common ion effect, when we talked about KSP. We saw that your solids dissolve less when there's a common ion in solution. Similar things happening here with buffers. So if you've already got some product present in the solution, then it's not going to dissociate as much. So that's another kind of perspective on buffers and like what's going on. It's a common ion scenario. All right, so look at this example. We're looking at how do buffers behave as buffers. So what's going on here? So we got a buffer that's made by combining you've got a weak base and its conjugate acid. And we know buffers maintain pH by neutralizing any acid or base that's added to the solution. So if you are to add some acid to your buffer, then the base in the buffer is going to neutralize any acid that you're added. It's going to turn that this H plus ion into NH4 plus. If you add base to your buffer, it's going to react with a weak acid component. So your base is going to react with your NH4 plus. That's going to make NH3 and H2O. So these are the two reactions that are responsible for your buffer kind of maintaining its pH. So the base present in the buffer is going to neutralize any acid that's added, and the acid present in the buffer is going to neutralize any base that's added. All right, so here's another scenario. What if we want to figure out the ratio of acid to base needed to create a buffer with a pH of 4? So think about what we know. We know we want our solution to have a pH of 4. We know it's a buffer, so we can use this equation, pH equals pKa plus log of A minus, which in this case, that's your fluoride, to HF, so your base over acid. We know the pKa, or we could figure it out, because the Ka is given right here. So the pKa is the negative log of 6.8 times 10 to the negative 4. So if you plug that in, 6.8 E for negative log, you get 3.17. So now we should be able to solve for this ratio here. So just kind of plug in what we know. So we know the pH is 4. We know the pKa is 3.17. And we're trying to find the ratio of F minus to HF. Before I solve, I'm just going to point out that the pH is greater than the pKa. So I expect to have more base than acid present, since the pH is a little bit higher, right? And bases make the pH higher. So just, it's good to stop and do some kind of a mental math, little approximation before you go too far here. So if I stop and rearrange though, subtract 3.17 from both sides, end up with 0.83 equals the log of F minus over HF. So I'm going to raise both sides to the power of 10. And I end up with this, that the F minus to HF ratio is 6.8. So basically, your F minus concentration should be 6.8 times that of your HF concentration in order to make a buffer with a pH of 4. So we definitely need more base than acid to make this pH higher than the pKa here. Here's a similar question here. Looks like we got a buffer because we got sodium benzoate and benzoic acid. So we got a buffer, so we can use this equation, pH equals pKa plus log of A minus over HA. And let's start plugging in what we know. We know the pH, we want it to be 4.25. The pKa, we're going to go take the negative log of this right there, so 6.5. 6.5 times 10 to the negative 5th. Take the log of that, you end up with 4.19 as your pKa. And then your log of, we don't know what the base concentration is, but we do know that the acid is going to be 0.2 molar. So we can rearrange here, 4.25. So we end up with 0.06 equals the log of the A minus concentration divided by 0.2. So we raise both sides to the power of 10 there. So you end up with 1.15 equals your A minus divided by 0.2. So 1.15 times 0.2 molar is going to give us your A minus concentration. So A minus is going to be 0.23 molar. Okay, but I don't want to just find the molarity. I want to find the mass. So this actually is going to be a few more steps here. So to find the mass, we first have to find moles. So we have to do 0.23 molar times the volume. And so the volume's 0.15. So you end up with 0.035 moles of sodium benzoate. And then you're going to use the molar mass of sodium benzoate to find grams, which I am not going to look up right now, but you could look that up. Okay, so sodium benzoate, sodium, and then this would be the benzoate ion. That's what sodium benzoate is. But you get the general idea here of how you want to solve this problem. Okay. So here's a good one. Which is a buffer, yes or no? Tell us why. Okay, so this first one is definitely yes. You've got NH3, NH4 plus, definitely yes. This one, we've got NH4 and hydroxide. So your initial thought might be no, because I don't have a weak acid in its conjugate base. But if you look at the amounts here, you've got more NH4 than you have NaOH. So what's going to happen is any NaOH that you add is going to react with your NH4 and turn it into NH3. And as long as you have excess NH4 present, along with some NH3, then you have a buffer. So this is actually a buffer. And the other way you can think about it graphically is if you think about a titration curve, it's like you're titrating a, let's see, we started with a weak acid, NH4 plus, you're titrating it, and you're stopping over here somewhere before the equivalence point. That means you've made a buffer. So if you titrate a weak acid and stop somewhere before its equivalence point, you're going to have a buffer. You'll have a combination of a weak acid and its conjugate base. All right, let's take a look at this one. This is a weak base plus a strong base. So those are both bases, so that's not going to work. This one here is a weak acid and a weak base, whoops, and a strong acid. So I'm going to keep in mind, well, those are going to react. Let's see. So we add these together, NH3 and H plus, it is going to form the conjugate acid, NH4 plus. And since we have more NH3 than we have HCl, you're going to have excess NH3 present in the solution, and you'll have formed some NH4 plus. So you will end up with a buffer here. So what's happening here is you're starting with pure weak base, and it's like you're titrating it here to the half equivalence point. So that's another way you can make a buffer, is by titrating a weak acid to the half equivalence point or titrating a weak base to the half equivalence point. All right, E is not a buffer. It's a strong acid and a strong base. This one is a buffer. Again, same kind of thing here. You have titrated a weak acid to about its like half equivalence point. It doesn't have to be exactly half. Just anywhere before equivalence, you're going to have a buffer anywhere in this kind of region right here. This one right here is also going to be a buffer because this one's a combination of a weak acid and an ionic compound containing the conjugate base there. And then if you look at this last one, this one is a weak acid and a strong acid, so that one is a no. All right, so the main takeaway here is the ways you can get a buffer is by adding a weak acid and its conjugate base, or you could titrate a weak acid to its half equivalence point, or titrate a weak base to its half equivalence point. Those are some kind of main ways you can make a buffer. All right, and then you want to figure out, we also want to identify which acid-base pair is the best choice when you're trying to make a buffer with a certain pH. So the target pH should be close to the pKa of the acid. So if I want to make a buffer with a pH of 7.2, I want to choose an acid that has a pKa of close to 7. So it looks like this one right here, hypochlorous acid, is going to have a pKa closest to 7, because yeah, its exponent is 8. 8's close to 7, so it's going to have a pKa close to 7. I can do the math and figure out what it is exactly, but I can also just kind of predict what it is based on that exponent there. So I want some hypochlorous acid and its conjugate base right there. All right, what if I want a pH of 9? So I want to choose an acid that has a pKa close to 9. So that could either be ammonium would work or phenol would work. Let's see, what are my options here? Ammonium is one of my options right here. So that's going to be my best choice there. So NH4 plus is my weak acid, NH3 is my conjugate base. The pKa is close to 9, so it's going to make a good buffer. And then last question here, thinking about, is pH equal to pKa, is a little bit above or a little bit less for the following mixtures? So in this case, if your amount of acid is greater than the base, the pH is going to be less than the pKa. In this scenario, it looks like your amount of acid is less than the amount of base. So if you have more base than acid, then the pH is going to be a little bit greater than the pKa. And in this case, oh, so here we've got a little titration happening. So we've got 0.1 moles of HA, and you added half as much hydroxide. So what you'll end up with here is you'll end up with half of your HA will turn into A minus. So they'll have equal amounts of your weak acid and the conjugate base. So the pH is going to be equal to the pKa. And then this last scenario, let's see what happens here. You're going to end up with, you start with 0.1 moles HA, 0.075 of it is going to turn into A minus, and you'll be left with 0.025 in the original form. So this scenario, your A minus concentration is greater than your HA, so your pH is going to be greater than your pKa. And if you think about this in terms of like a titration curve here, initially you've got pure HA, and then you've got your, at equivalence point, you've got pure A minus. If you're exactly at the halfway point, your HA and your A minus are equal. And my graph isn't very accurate here. I should maybe make it looking more like this. Okay. Over here, you should see that when you have more A minus than HA, the pH is a little bit higher. And over here, where you have more HA than A minus, the pH is a little bit below the pKa. That's what I was trying to show here with my rough sketch. Okay. All right, hope this helps.